Hi everyone, this is me Yashivani here, and I'm back with the part 2 of our chemistry plus 2 chemistry, the chapter solutions. So hope all of you have prepared very well with the part 1 of solutions. That is, we have in the part we have discussed about solution, what is solution, what is binary solution, what is aqueous solution, and what is non-aqueous solution, the different types of solutions like gaseous solution, solid solution, liquid solutions, and on the basis of what we classify those solutions into gaseous, solid, liquid. Yeah, tell me on the basis of what. Let me take the example of gaseous solution. So tell me the state of solvent and solute in it. Let me see if you guys have studied something from part 1. Okay, first of all, let me tell you that be systematic. As I've already posted part 1, you must study part 1 very clearly, then come to part 2, or else you'll get nothing. You literally get nothing about part 2 or the things which I'm discussing here. So tell me, what is the state of looking this. Okay, tell me the state of solid and solvent in gaseous solution. Yeah, okay, fine. That's great. The solvent will be in the state of gas, and solid can be either solid, liquid, or gas. Okay, so the state of solvent decides the state of solution. In the solid solution, the state of solvent will be solid. In the liquid solution, the state of solvent will be liquid. And after that, we have discussed about concentration, the methods of expressing concentration of solutions, or the solute dissolved in particular solvent making solution, that is mass by volume percentage, mass percentage, mole fraction, then ppm, parts per million, molality, seven types or seven methods of expressing concentrations. Hope you're all are familiar with those methods. So practice some more questions from mole fraction, molarity, and molality. That's actually seen in many of the question papers. The questions will mostly be from this mole fraction, molarity, and molality. Okay, I've already given some questions to you. Like we have done a question from mole fraction here. Okay, just uh, be prepared with this type of question. You can expect mole fraction type questions from mole fraction like this. And also we have discussed about the question of molarity and molality. Okay, now in the last class I actually forgot to tell you one concept. We'll be talking about that concept first, and we'll be moving on to the further topics today. So before starting today's class, I just wanted to tell you some tips, okay, to appear for your exams. How to appear for your exams. So this is not just tips, but I've actually made practical in my life, and I've found great results from it. So before appearing for your exams, either your terminal exams or midterm exams, whatever it is, so drink some cold water between, not in between, before you enter your exam hall, and have a piece of chocolate. Okay, you might have many favorite chocolates like Dairy Milk, Bounty, or what Mars, whatever it is. Eat a piece of chocolate, have some cold water, and enter your class, enter your exam hall, and appear for your exams. Because there are many students who actually study well, prepare well for the examination, but when they enter the exam hall, what problem they face is that they don't actually get the right answers for the questions, or they find difficult, or they find trouble to actually get the right answers for the questions. They might have studied and they might know, like, okay, this page number, this side, with that figure, but I don't know, I don't actually remember, I'm not able to get that answer. So if you don't want to face this type of problem, try this. I don't know, I'm not sure whether it will be successful in your case, but it was and it is always a success in my case. Okay, before appearing for exams, I usually try these things. So drink cold water and eat a piece of chocolate before you enter your exam hall, so that you won't face such kinds of problem. But if you don't study anything and enter exam hall, I don't know, this chocolate and cold water won't help you. Okay, so just because of dairy milk or chocolate or cold water, you're not going to pass the exam. Hmm? Uh, that's not an easy trick, but if you have studied everything and you're not still not able to figure out things, you can try this. Also, when you wake up early in the morning to study or to work out, to do exercise, first have a spoon of ghee. Ghee is actually rich in fat. Okay, fat is very essential for your brain. Even chocolates have large quantity of fat. So fat is really essential for your brain, and I recommend having ghee also. A spoon of ghee every day before having coffee or tea. Fine. So let's get into our class, today's class. So in the last class, I've got to tell you about a particular concept. So tell me, what is molarity? We have already studied what is molarity and molality. So molarity means capital M, number of moles of solute by volume of solution in liters. What is molality? Number of moles of solute by mass of solvent in kilogram. Mass of solvent in kilogram. So the question may come like this. In molarity and molality, according to you, which is a better method to express concentration? Listen to the question first. In molarity and molality, according to you, which is the best or better method of expressing concentration? Or else the question can come like this. Uh, which is temperature dependent? Molarity or molality? Or the question can come like this. Which is temperature independent? Molarity or molality? What do you mean by temperature independent? Temperature independent means whatever or wherever the temperature goes. Okay? The concentration term remains constant. No matter the temperature increases or decreases, concentration term remains the same, or it is a constant. That is temperature independent. If a concentration method or method of expressing concentration is temperature dependent, it will change as the temperature changes. Fine. If the temperature increases, there will be a change in the concentration term or the value of concentration. If the temperature decreases, there will be a change in the value of concentration. So that is called temperature dependent. So in molarity and molality, tell me which is temperature dependent on temperature independent. And obviously, if a value is changing with temperature, we can say that that's not a better method. Obviously, if you're entering a physics lab or chemistry lab, you need constancy in your answers, right? Okay, whenever you measure something, okay, there must be a constant value for anything. So think the case of this. If it changes with some external factors, can you say that it's a better method? No. Whatever the condition is, the if the result remains same, we can say that the method used is better or best. So in molarity and molality, the method of concentration which is temperature independent is said to be the best one or a better one when compared to the other one. So in molarity, we can see that volume comes here. Volume. Volume is obviously temperature dependent. As temperature changes, there will be a change in volume. In molality, we can see that mass. Mass comes in the denominator section. It is temperature independent. So tell me which is better method of expressing concentration. Obviously molality, because molality, the mass term, is independent of concentration, independent of temperature variations. But in molarity, we have volume. Volume is obviously temperature dependent. It changes with temperature. So this concept was actually based on the topics which I discussed in the last part, but I actually forgot to explain the topics, the particular topic in last class. My mistake. So in this class today, we're going to complete about 2 by 3rd of the chapter. Hopefully, yes. Shall we start? The first topic is solubility. What is solubility? You might have heard the term solubility. So tell me, what is solubility? Consider there is a glass of water in my hand, pouring sugar or let it be salt. I'm pouring some salt into it. So what happens in that solution. Yes, salt dissolves in water, right? Okay, I again pour some salt into it. Yes, salt dissolves in water. And I pour and pour and pour and pour and pour. At some point, I cannot pour more salt into it because the salt doesn't dissolve in water. That point is called saturation point. Saturation point is a point at which no matter how much quantity of solute I add, when the solution reaches the saturation point, the solvent cannot accept any more solute. In the case of salt solution, I'm adding salt into it. Okay, in the initial stages, water can absorb salt or water can dissolve salt. Okay, water can dissolve salt. Okay, for gradually when I add more and more and more and salt, at some point the solvent, that is a water, says no, I can't. I can't dissolve any more salt. I can't dissolve. This is my maximum level. So please leave me alone. I can't do this again. And that point is called saturation point. Saturation point is a point at which the solvent cannot dissolve any more solute. After the saturation point, if I add some salt, what will happen? It will settle there. It will settle there in the solution, but it won't dissolve. It will settle there, but it won't dissolve. So let's see what is solubility. Solubility of a substance is its maximum amount that can be dissolved in a specific amount of solvent. So in the case of salt solution, the maximum amount of the maximum amount of salt that can be dissolved in water is called the solubility of that substance. Maximum amount of salt that can be added or that can be dissolved in the solvent, that is water, is called the solubility of the substance. If I go to a restaurant, okay, I order my favorite food, let it be paneer butter masala and butter naan. Okay, you might have many other favorite foods. Yeah, I do have that. My favorite food is paneer butter masala and butter naan, but there are many other foods too. So, oh, that's not a matter. Okay, fine. I go to a restaurant. I order paneer butter masala and butter naan. I'm waiting for the food, right? I'm in hunger and I'm waiting for the food. In that state, I can have as much as food I want, right? Okay, the waiter comes. He's coming with my favorite food. He places that on my table. So I started having food. Okay, I started having food, and it gradually is dissolving in my stomach. Okay, guess my stomach is the water in salt solution, that is a solvent, and the food is the salt, that is the solute that I am adding to the solvent. I'm having paneer butter masala and butter naan. At some point I feel like, okay, my stomach is full, I don't want any more. No, I can't have any more, my stomach is full. That point is called saturation point. At that point I can't have any food, right? Okay, the same case is happening in the case of salt solution. The point at which solvent cannot dissolve any more solute is called saturation point. And the solutions which have already acquired that stage is called saturated solution. Fine. Solubility means the amount of solvent, the amount of solute that can be dissolved in a particular amount of solvent. In what is the solubility of mine? What is my solubility? If I've ordered something and I started having it, and at some point I feel like, no, I can't have any more. From the initial stage of having food till the point I said, no, I can't have any more, that is solubility. That is my solubility. So from the point of dissolving the very first spoon of salt into a solvent till the point at which it can't dissolve any more solute or any more salt, that is solubility of the salt solution. Fine. The solubility of a substance means the maximum amount of solute that can be dissolved in a solvent. And what is saturated solution? Saturated solution means the solution in which no more solute can be dissolved, or the solution which has already acquired the saturation point. What is unsaturated solution? That's the next question. What is unsaturated solution? I've already told what is saturated solution, so you tell me what is unsaturated solution. Yes, obviously the solution in which more solute can be added. Okay, a solution is saying, okay, add some more salt into me. Yeah, come on, add sugar, yeah, add sugar. So this solution is actually unsaturated. If I go to a restaurant, I have and have and have more food, and still I say, Bhaiya, take a chapati for me, Bhaiya, a roti please. I'm in the unsaturated state. Okay, and if I say no, I can't, I'm loaded. Okay, my stomach is full. That is my saturated state. Okay, the same is happening with the solution. Next is like dissolves like. Okay, you know about likes in Instagram, Facebook, YouTube, Twitter, everything like. Like that. Here, like means, yes, I've added sugar to a glass of water. So water dissolves sugar, right? Even water dissolves salt also. So in both these cases, polar solvents uh, are mixed with polar solutes, or polar solutes are dissolved in polar solvents. Let me tell you one more thing. Guess I'm adding salt to water. Water is H2O, right? It's a polar solvent. Salt, NaCl, it's a polar solute. So always a polar solute can be dissolved in a polar solvent only. Here examples are given. Polar solutes like NaCl sugar are soluble in polar solvents only, like water. Like water. Now take the case of non-polar solutes and non-polar solvents. Always the non-polar solvents dissolve non-polar solutes, or the non-polar solutes are always dissolved in non-polar solvents. Non-polar solutes like naphthalene are soluble in non-polar solvents like benzene, CCl4, etc. Non-polar solutes like naphthalene is always soluble in non-polar solvents like naphthalene, carbon tetrachloride, etc. So a polar solute cannot be dissolved in a non-polar solvent. A non-polar solute like maybe in water. Water is a polar solute. I can't dissolve oil in it because it's a non-polar solute. So non-polar solutes cannot be dissolved in polar solvents. Fine. Next is the effect of temperature and pressure in solubility. In these cases, we are learning about solid in liquid case. We are actually learning about solid in liquid case. So in solid and liquid, the solubility, how the solubility is related to temperature and pressure is what we are going to look now. Effect of temperature on solubility in the case of solid in liquid. When solid is a solute and liquid is a solvent, in such a case, the effect of temperature on solubility. You might have learned about Le Chatelier principle in your previous classes. We don't have to go in depth about Le Chatelier principle, but just keep in mind an exothermic reaction is a reaction in which heat is given out or heat is released. Endothermic reaction is a reaction in which heat is absorbed. Okay, in the case of endothermic reaction, heat is absorbed. So when temperature increases, solubility obviously or automatically increases. In the case of exothermic reaction, when temperature increases, that is a reaction in which heat is given out or heat is releasing. In such a case, when temperature increases, solubility increases or decreases. Look into the screen. Increases or decreases? Decreases, yes. So, an exothermic reaction is a reaction in which heat is given out. In such a case, when temperature increases, solubility will not increase, it will decrease. But in the case of endothermic reaction, heat is absorbed. Hence, when temperature is increased, solubility is also increased. And what is the role of pressure on solubility? We are saying about the case of solid and liquid. Okay, solid dissolved in liquid. So tell me, whether solid and liquid, both of them are compressible or non-incompressible. You have already learned the chapters and basic concepts of chemistry in class 11. In the chapter, you have already learned about the properties of three states of matter, that is solid, liquid and gas. So you might know the solid and liquid is compressible. They are compressible or incompressible. Yes, they are incompressible. So there's no effect of pressure on solubility of solid in liquid case. Solid dissolved in liquid, in such a case, solubility doesn't depend upon pressure, but solubility depends on temperature. As solid and liquid, they are incompressible, they have no effects on pressure. Fine. Even if pressure changes, they are incompressible, and hence they have no changes. The solubility has no change. But as temperature increases, in the case of exothermic reaction, solubility decreases. In the case of endothermic reaction, solubility increases. Now we are moving on to Henry's law. Henry's law, in Henry's law, we are discussing gas in liquid case. Till now we have discussed solid and liquid case, and now we are going to discuss gas in liquid case. Okay, so consider consider a bottle filled with Coca-Cola. Okay, so you know that carbonated drink is Coca-Cola is a carbonated drink. So I need to pass carbon dioxide into Coca-Cola. How can I pass carbon dioxide? I just blow into it carbon dioxide, or release carbon dioxide. All human beings release carbon dioxide. So I just want to blow carbon dioxide into it. No, I need to pass carbon dioxide into Coca-Cola at high pressure. High pressure. Why do I need to do that? Carbon dioxide is a gas, and Coca-Cola or any liquid is or any solution is in the form of liquid. Okay, so whenever I need to pass a gas into a liquid, so as to increase the solubility of the gas in that particular liquid, I need to increase the pressure. At high pressure, at very high pressure, I pass carbon dioxide into that particular solution and seal it. Okay, such things are called carbonated drinks. Carbonated drinks have carbon dioxide passed into a solution at high pressure. Okay. Beforehand, let me tell you that carbonated drinks are drinks like Coca-Cola, Pepsi, Sprite, or whatever it is. I actually don't promote such things. So even if you are having such things with biryani or any kind of food, I prefer not to have, and even you guys should prefer not to have such drinks, because it's really injurious to health, really harmful to your health, and you already know the side effects of having such carbonated drinks, right? Even if you know the side effects, even if you know the demerits of such food items, you'll still have it, I know. Anyways, limit yourself from having such cool drinks. Okay, so in carbonated drinks, I pass carbon dioxide at high pressure into the solution so as to dissolve, so as to make the gas highly soluble in that particular solution. So here, as I increase the pressure, the partial pressure of gas, solubility increases, right? Solubility increases. Solubility of a particular gas increases as the partial pressure increases. As I increase the pressure of carbon dioxide, okay, the solubility of carbon dioxide in the solution or in the carbonated drink increases. So solubility is directly proportional to partial pressure of the gas. Now, partial pressure of the gas is directly proportional to mole fraction of the gas. Consider two glasses. I have some solutions in it. Okay, I have some solutions in it. I'm applying a pressure P here. I'm applying a pressure 4P here. Obviously, this container which has 4P pressure, the gas in it will highly be soluble. Okay, and the mole fraction will be high. Mole fraction will be high. So from this relation, partial pressure directly proportional to mole fraction, I can derive the Henry's law. What Henry's law says is that the amount of a gas dissolved in a liquid at a given temperature is directly proportional to the mole fraction of the gas. So that is the law here. That is the law given here. Partial pressure of a gas directly proportional to mole fraction, that is chi. Hand. Okay, partial pressure directly proportional to mole fraction, and hence I need to remove the proportionality. I give a proportionality constant. That is called Kh into mole fraction. H should be written down, okay? It's a subscript actually. So Kh into mole fraction, where Kh is Henry's law constant or Henry's constant, and this is mole fraction, this is partial pressure. The volume or the amount of gas dissolved in a particular liquid at a given temperature is directly proportional to mole fraction of that liquid. The partial pressure of that gas. Okay, the amount of gas dissolved in a particular liquid is directly proportional to the partial pressure of that gas. Amount of that gas dissolved in a liquid means the mole fraction itself. It is directly proportional to the partial pressure of that gas. P equal to Kh into mole fraction, where P is the partial pressure, Kh is a Henry's law constant, and chi is the mole fraction. Fine. Is the law clear? Let me explain once again. This law is very, 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 very important. Questions can come very directly from this topic. They'll ask you state Henry's law. So how will you state it? Tell me, how will you state it? You need to know the equation first of all. P equal to Kh into mole fraction. Then denote the terms also. P is the partial pressure, Kh is a Henry's law constant, and chi is a mole fraction. Now state the law. The amount of a gas dissolved in a liquid at a given temperature, that is the mole fraction itself, is directly proportional to partial pressure of that gas in that liquid. Fine. Or else you can give this definition. Mass of a gas dissolved per unit volume of a solvent at a given temperature is directly proportional to the mole fraction, or the pressure of the gas in the equilibrium with the solution. That is the relation given above. Mass means directly proportional to the amount of gas, or it's directly proportional to the mole fraction. So either you can denote like this, or you can denote it as it is given in the PDF or the screen. Now, the graph of Henry's law. It's very, very, very important. So the equation of Henry's law is P equal to Kh into mole fraction. You know the equation of straight line, right? Y equal to mx plus c. Here in the state position of c, I'm putting 0. So see, P equal to Kh into mole fraction. It is similar to the equation of a straight line, y equal to mx plus c. So when we plot the Henry's law in a graph, you need to take the partial pressure in the y-axis and mole fraction in the x-axis. So it will be a straight line passing through the origin. Okay. Now, I'm giving a question for you all. This is a graph where I have 3 solutions. Let it be A, B, C. Okay. Here I have partial pressure P, and here I have mole fraction. The question is, which one is going to have high solubility? Which one is going to have high solubility? Either A or B or C. Tell me. So the concept which will help you to answer this question, I haven't given you the concept. So anyway, I'll give the concept right now by answering to this question. Anyway, you may please think the relation between solubility and this graph. Let me see if you guys get it. The question is, which one is going to have high solubility, either A or B or C? Fine. See this equation. In the place of m is a slope. You know what is m, right? It is the slope of a straight line, y equal to mx plus c. So in the case of the equation of Henry's law, in the place of m we have kh. So we can say that slope and kh is same. Now let me tell you the relation between kh, Henry's law constant, and solubility. Kh is directly proportional to 1 by solubility. Or we can say that KH is inversely proportional to solubility. So as KH increases, solubility decreases. As KH decreases, solubility increases. So in comparing these two equations, we can see that in the place of slope or in the place of M, we have KH here. So we just need to find the slope of A, B and C in this particular graph. Slope M equal to tan theta, right? Tan theta or dy by dx. You have already studied in class 11. So here, this is a theta 1 of A. For B, we have this much of theta. Let it be theta 2. For C, I have large degree of the slope, theta 3. So as theta increases, tan theta increases. As tan theta increases, slope increases. Slope increases means KH value increases, solubility decreases. So tell me, for A or for B or for C, the solubility is high. Or we can say the slope is very less. Slope is very less. Yes, A has greater solubility, then B, and then comes C. C has very less solubility because the slope is very high. Tan theta is high, so KH is very high, hence solubility is very less. Now let's see some conditions at which Henry's law is applicable. So for Henry's law to be applicable, we have few conditions. We have 3 conditions. The temperature shouldn't be very less and the pressure shouldn't be very high. And also the gas shouldn't undergo any chemical change or any dissociation or association. So first of all, the pressure shouldn't be very high and the temperature shouldn't be very less. Second, gas shouldn't undergo any chemical change. Also, the gas shouldn't undergo association or dissociation. Chemical change means the changes to its chemical properties. Association, dissociation means association of atoms or moles of the reaction. And dissociation is just opposite to association. So the gas shouldn't undergo chemical change, it shouldn't undergo association, it shouldn't undergo dissociation. Also, the temperature shouldn't be very less and the pressure shouldn't be very high. In these conditions, we can apply Henry's law. Now moving on to some applications of Henry's law. I've already discussed one of the applications of Henry's law, that is carbonated drinks. Carbonated drinks. To increase the solubility of CO2 in soft drinks, what we do? We pass CO2 with high pressure and we seal it, right? So one of the applications of Henry's law is in carbonated drinks. The second application of Henry's law is among the scuba divers. So let me explain the case as a story. Consider a scuba diver is here. Here the pressure is very less and the scuba diver goes from here, from the surface of the water to the underwaters, and in this region the pressure is very high. Okay, as a scuba diver goes from the surface of the water to underwaters, as it goes down, the pressure increases, right? Pressure increases. So he'll feel difficult to breathe. So as to overcome such condition, we have air tanks, right? Air tanks are provided to scuba divers so as to overcome such conditions. In the air tanks, we dilute helium. Air diluted with helium is provided. Why? At the lower surfaces, okay, at the lower surfaces of water, that is here, the pressure is very high and hence the solubility of gases is very high. We are discussing the case of gas in liquid. In the earlier stage, we have discussed the case of solid and liquid, but for both solid and liquid, pressure has no role in its solubility. But here we are discussing about gas in liquid. Gas has a role and gas has a relation with pressure. As pressure increases, the solubility of gas increases. So as he go down, okay, the pressure increases, so the solubility increases. Solubility of gases increases. So now he thinks like, okay, I want to go to the upper surface of the water. He soon goes. What will happen? There happens the condition of bends. BENDS. It's a physical condition where the patient or the person going from the lower surface to the upper surface of water may die or may feel pain to the nerves or blood vessels. Okay, it's due to the pressure change and the solubility of gases, therefore. Okay, so in this condition also Henry's law is applicable. And if you want to know more about bends, the condition of bends, here we don't need much explanations to bends, okay? If you are in need of further explanations, you may please check Google. And you can also see few pictures of bends, the condition bends. And there is a third application to Henry's law, that is anoxia. Anoxia. As a person goes uphill, okay, this is a mountain. The person is here. Here pressure is actually high. As he goes from here and reaches here, pressure is very low. Right? Pressure is very low. In this condition, he may not be able to think properly, and blood may come out of his nose. This condition is called anoxia. Because the less solubility of gases, as we go high, the pressure is very less and the gases won't be soluble high enough. And a condition called anoxia can happen. Fine. So these are the three applications of Henry's law discussed in your textbook, NCERT textbook. One is about the carbonated drinks, other is about bends, and the third one is about anoxia. Now, aquatic species live more comfortably in cold water than warm water. This is a question which is frequently asked in your question papers for your board exams. So tell me, why are these aquatic species preferring to live in cold water than in warm water? I've already said, consider this as water. This is the upper surface, okay? This is the upper surface, this is the lower surface. Here, pressure is very less. Here, pressure is very high. Here, temperature is very high, and in the lower surface, temperature is very less. So as temperature decreases, the solubility of gas increases. Solubility increases. Solubility of gas increases in two conditions: when temperature is very less and pressure is very high. When temperature is very less and pressure is very high. So in the lower surfaces of water, there is a cold area, and there temperature is very less. So the solubility of gases will be very high, and hence the fish or the marine creatures will be able to breathe very easily. So they prefer to live in cold area than in the upper surface or the area with high temperature. Clear? Now we are moving on to the case of liquid in liquid solutions. Liquid in liquid solutions. Fine. So tell me, what is vapor pressure? Have you heard about vapor pressure before? No? You haven't heard about vapor pressure? Fine. I have a glass here. In this glass, I filled it with volatile liquid. Volatile liquids. What is volatile liquid? I'm sure you have heard about volatile liquids before in your class 11th. Right? Volatile liquids are those liquids which have a tendency to evaporate. Right? They have high degree of evaporation, high degree of vaporization. So volatile liquids have a tendency to evaporate. Right? So I'm filling this container with volatile liquid. If I'm not sealing the container, what will happen? The volatile liquids will turn to vapors and escape. Right? So I'm going to seal this container. I've already sealed this container, and I've filled it with volatile liquid, right? Volatile liquid. Here is a volatile liquid. What will happen? Volatile liquids have a tendency to evaporate, right? So it will obviously form vapors here. Are you able to see this? Yeah, almost. Should I draw it more neatly? Okay, I'll draw it more neatly. I have a container. Let this be the container. I have a container. I'm filling it with volatile liquid, okay? Volatile liquid. This is a volatile liquid. I'm going to seal this container so that the volatile liquids won't be able to escape. But still, the volatile liquid has a tendency to evaporate or has a tendency to escape. So what will happen? The volatile liquid will form vapors. Vapors all over the container. These are the vapors, okay? So these vapors will exert a pressure to the container. And this pressure is called vapor pressure. Vapor pressure is a pressure exerted by volatile liquids. Clear? Pressure exerted by vapor above the liquid surface in equilibrium with the liquid phase at a given temperature. Means what? Pressure exerted by vapor. So these are the vapors. The vapors exert a pressure to the lid of the container, right? When it is closed, when the container is closed, and I fill it before closing I fill it with volatile liquids, and I close the container or seal the container, the volatile liquid have a tendency to evaporate or escape. So it will form vapors all over the container, and the vapors will exert a pressure to the container. So pressure exerted by the vapor above the liquid surface. It's a volatile liquid. Above the liquid surface there will be vapor. Okay, this vapor exerts a pressure to the container or pressure to the lid or to the surface, upper surface, and this is known as vapor pressure. Vapor pressure. Vapor pressure can more be defined as, or better be defined as, the tendency to escape or the tendency to evaporate and leave. Okay, tendency to escape or tendency to vaporize and leave. Fine. Now we need to see the effect of temperature in vapor pressure. So consider the case of your home itself, when you're not surrounded by your parents or the members at home. When they leave your home for a function or for shopping, you'll be alone at home, right? So in that condition you have a greater tendency to do something mischievous. When nobody is watching you, you have greater tendency to do something mischievous. Same thing is happening with the liquid in liquid condition. Okay, what will happen when temperature increases? The volatile liquid has a greater tendency to escape. Okay, means vapor pressure increases. When temperature increase, the molecules, the volatile liquid, they have higher kinetic energy, and the molecules will be running, and they have higher tendency to leave the surface of liquid or leave the container. They have high escaping tendency. So as temperature increases, the vapor pressure of volatile liquids increases. As temperature increases, vapor pressure increases. All right, done, set. So today we have discussed about solubility. What is solubility? And what is saturated solution, unsaturated solution in the case of like dissolves in like. Then we have discussed about the effects of temperature in solubility. Two cases we have discussed today mainly, the solid in liquid case and gas in liquid case. In solid in liquid case, temperature has effect, but pressure has no effect. As temperature increases, solubility increases in endothermic reaction, but solubility decreases in exothermic reaction. This is about the solid in liquid condition. Okay. Coming to gas in liquid, we have Henry's law here, and we have also already stated the Henry's law. We have seen the graph of Henry's law here. We have also solved a problem and the conditions at which Henry's law is applicable, and the applications of Henry's law, and also a question regarding that. And finally, we have come to the case of liquid and liquid condition. In liquid condition, we have few more laws to be studied. That's Rolle's law and Dalton's law. So that concepts will be discussed in further classes. So today it's time to wind up this class. Hope you have enjoyed today's class. Be prepared for the next class by learning all the concepts which I've taught you today in part 2. Ready? Okay, till then, bye.